Hey guys, my name is Adrienne and welcome to Organic Chemistry 1, Part 5 of these recorded sessions. Today we'll be going over, for most of y'all, Chapter 5, but in general, stereochemistry. So a lot of 3D action going on, a lot of imagining and stuff like that. So here is our agenda for today. As you can see, we'll be going over isomers. We kind of saw a little bit of that in Part 1, achiral-chiral molecules, stereogenic centers, and stereoisomers. So all of these are going to be super useful with reactions because a lot of them, um, switch things up as you saw um, in the last part where certain reactions prefer certain things, right? Like always, right? So let's get started. So we know what isomers are. We know we saw the first part of the isomers in part one, um, but we'll recap. Isomers come in constitutional and stereoisomers, right? So we know constitutional, and then we have stereoisomers. Okay. So in general, isomers are different molecules, same formula, right? Get this out of the way. Same formula. Right. So now it's kind of broken down into two categories: constitutional, stereoisomers. Constitutional being structurally, right, structure-wise. So it got moved or shifted, right? Like the bonds got shifted, but it's still the same formula. But now instead of the halogen being here, it's over here. So something moved, right? Structure, um, and this requires um, breaking bonds, breaking. Requires breakup bonds. Okay, running out of room there. Okay, and but stereoisomers, you don't break anything. It's just 3D. So we know wedges and dashes. That's probably the only thing we'll see with the 3D wise, right? The halogen was pointing towards us, but now we rotated it, and that's pointing, um, you know, back here. So that's what they mean by 3D space, spatial arrangement, 3D arrangement. No break of bonds. So that's really the main difference between those two. And just a little bit more about these. For constitutional isomers, since it does require breaking, that makes, let me do this. That makes it have different properties, right? So since we broke that, we're breaking bonds, we're rearranging the structure, right? It's going to have a different name, so different nomenclature, right? Different name, um, physical and chemical properties, which makes sense, right? Because all those functional groups are now in a different place, so they're affecting environment differently, right? Different physical chemical properties, and then, um, but what do they have? They have the same functional groups, right? So basically, they're just moving. This alcohol is now in here, things like that. So, but with stereoisomers, pretty much everything is the same. Same name, um, same functional groups, same properties as well. So pretty much all the same. And the only thing different about the name is the R and S or the cis and trans, or things like that, right? So not too crazy. And even then, it's not even not even that big of a difference because everything's going to be in the same exact place, but now this wedge is now a dash, right? Same functional group, right? So there you have it. Kind of like a little, just a list of it, right? And now let's go to another page here to do some examples to kind of just put this to the test, right? These are what you need to know. And these are just these tidbits over here. They come with knowing that constitutionals, you break bonds, stereoisomers, you just twist them, right? Okay, so let's do practice. Let's do just a big ol' labeling. Labeling. Label either constitutional, stereoisomers, or identical. Okay, so I'm gonna give you a couple here. Let's see. Versus. Let's see what they happen. And you guys are probably answering this right off the bat because it's not too crazy. It doesn't get too crazy. Basically just pay attention to the dashes and stuff because that's the giveaway or like where everything is, where the substituents are, right? The functional groups, things like that. Okay, last one. Okay, so take a second, label all these pairs, and obviously they're in pairs because constitutional isomers you have to compare it to something. You have to compare, do these two are these two stereoisomers constitutional isomers, or are they just exactly the same, right? So for the first one, you should have gone constitutional, right? Because these are substituents, and you can see how one of them like just moved, right? This was at 2 and 3. Now they're at 2 and 4, right? So they just moved. That's what we're talking about with the breaking the bond. They moved this 3 over here, moved it to the 4, right? Broke it. Here we should have stereo, right? And this is super obvious because one of them literally just changed into from dash to wedge, right? This one should be constitutional because they broke this and moved it to over here, right? So broken. This one, what do you guys get? Constitutional, right? So this one's one of those not obvious ones because you kind of just have to count and make sure that they're even isomers in the first place, right? So we have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. Am I missing a carbon? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, yeah. So actually, these are none, right? So these aren't even isomers because they don't have the same amount of they don't have the same formula. So we'll do that 0. Okay, but if we did like, let's see, 1, 2, 3 over here, 1, 2, 3, 2, 6, 7, 8, 9, 10. If we turn this into an H, then these would be constitutional, right? So things like that. Um, with H equals constitutional, right? So I think I just missed the H. I think I was supposed to have an H there, but yeah. So as is, it's nothing. They're not isomers, but with an H here, it would be a constitutional isomer, right? So what about this one? Right, you should have gone identical, right? They're not constitutional, they're not stereoisomers, um, because literally this is the same as that, but they just flipped it, right? And that's not a stereoisomer because um, let's see, imagine this as just looking like this, right? It's literally just this, and that's identical. Um, you can twist it however many way, but since it only has that one um, substituent, it doesn't really matter because we know single bonds they spin, so technically these are both the same forms, right? They're just spinning, um, but these for sure are different because now we go from um, trans to cis, things like that, right? So not too crazy. Isomers, we'll get a little bit more on that later, especially with stereoisomers. So let's move on to our second one. Let's see, our second one is achiral and chiral. So this might be achiral, chiral. Might be a little bit difficult to like visualize, especially with my bad drawing. But we know that achiral is superimposable, right? Superimposable. So that means they go together, like socks, right? Um, socks, superimposable. Now with chiral, non-superimposable. So like hands. So this as they can't like stack together, but socks can. I don't have socks, but for socks you just flip it over or like rotate it or whatever, and then you're good. But with these, no matter how you rotate it, they're not superimposable, right? So that's what that means. And again, with a kind of easier way to do this is also, let me do it in different colors so it pops. And this is what what a lot of people forget, and they just get caught up in like, oh god, I have to do the mirror image, blah blah blah. I have to spin it, rotate it, whatever, right? Look at for symmetry. So achiral has symmetry, and chiral, chiral, chirality has no symmetry, no symmetry, right? So that's another thing with that. That's another thing to look for in molecules, especially when it gets super huge. This is an easy way to kind of eliminate all that. Now that's pretty much it with those. Nothing too crazy, but I think this example would be better off. Would be better explanation. So let's do one. So not too crazy, right? It's just basically definitions here. Let's do another label. Label achiral or chiral. So I guess we'll probably get these super quick, so you can probably just fast forward. Just kidding. Okay, that one's bad. So take a second, pause the video, label achiral or chiral. Okay, so I got achiral, chiral, chiral, achiral. And again, another easy way to do this, right, is all the symmetry, right? This one, we just cut it in half over here, symmetrical. This one, if we cut it in half, it's not symmetrical, right? Because these two are mirror images. And same thing over here, they're mirror images, they're not superimposable, right? Over here, this way, we're not cutting it down here, right? Because then that would be chiral, but we're cutting it over here. So if you cut it this way, that would have been chiral, but we could also cut it this way, right? So that's all you need to do. We didn't have to draw whatever, right? We didn't have to wrote. We didn't have to draw the mirror images or draw whatever, draw their counterparts, right? So look for symmetry. I think that's the easiest way. For the most part, you will be able to eliminate most of the questions just using symmetry. So don't forget about symmetry. Okay, so that's super quick, super easy. Let's go on to. I feel like this video is going too fast. I need to stretch it out. Okay, so let's go with stereogenic centers, and this is where a lot of the things you guys will do with reactions, and even in Alchem 2, um, these are probably the most important. So, stereogenic centers. And stereogenic centers, we know that they have their centers with 4 different groups. Different groups. So it can't have anything. It can't have 2 of the same group. So it can't have 2 hydrogens or whatever. It can't have 2 methyl groups, right? It has to be 4 different groups, and that's the thing with stereogenic centers. And stereogenic centers, um, some molecules have a lot, some molecules have none, right? And sometimes they ask you how many stereoisomers of this molecule you have. So the way you to find that is number of stereoisomers equals is 2n, n being number of stereogenic centers. So stereogenic centers, so 2 to the n. So if you have 2 stereogenic centers, you'll have 4 stereoisomers, right? So not too crazy, just a little bit tidbit. You guys don't really use it, but there's always that 1 or 2 questions that are random that ask this. But 2 to the n, that's all you need to know. And with stereogenic centers is that no, I'm just going to put SC from now on. No SC equals not chiral, right? So we're not saying it's achiral, but it's definitely not chiral, right? And then 1 or more stereogenic center is chiral, and then 2 plus stereogenic center equals may or may not be chiral, depending on, and we'll talk about it later, depending on if it's RS, right? Things like that. May be chiral, right? So things like that. So this is what you kind of have to look for. And we talked about 4 different groups, things like that. So now the fun part is the configuration. So this is what they're talking about. Maybe chiral. How do we tell, right? So let me erase it for a new page. Stereogenic centers. So now we go into, you guys probably don't use this in class, but it's called, for RNS configuration. Oh, I misspelled that. Configuration. So configuration. RNS configuration is obviously the you know, either you're rotating left or right, right? So with RNS configuration, R rotates to the right, right? And this is where I had arrow, so is the right, and S is rotating to the left. So that's kind of um how I differentiate these. Oh, you guys can probably draw it way better, but R is going to the right, and S going to the left, left, right. So with RNS configurations, we prioritize the most the heaviest group, heaviest group per atom, and we'll talk about that later. Actually, we'll talk about that now. And this is called the this definition, a very loose definition, I might add, is the Kahn-Ingold prelog. Sometimes professors use this, sometimes they don't, but it's Kahn-Ingold prelog, and it's just pretty much prioritizing the heavier atoms per atom, right? And what I mean by per atom is that, let's do an example. So we know stereogenic centers, to have an RNS configuration, you need 4 different groups, right? So let's start off with something like Br, OH, just a methyl group or an ethyl group, and then let's say an H. So how do we prioritize this? So first, we said prioritize heaviest group per atom, so atom by atom. This is what I mean by that is that we're comparing this versus this versus this, um, versus this, right? Because we're looking for this. So now between oxygen, carbon, carbon, um, actually, let's do the H on this one because I think it was not meant to be a methyl group. It was I drew that crooked, so oops. Okay, hopefully you guys aren't hearing that, but so I'm just gonna keep talking so until it stops, until the background noise stops, and that's a mower. Sorry about that. But yeah, so atom by atom, we're prioritizing them. We're gonna prioritize them. So basically, we're comparing oxygen, right, versus carbon versus carbon versus hydrogen. So which one of those is the heaviest? The oxygen. So that's a 1, right? And you notice we didn't go all the way up to here because we said atom per atom. So now let's move on to our next atom. We have another carbon here, and we have another carbon here, and we have H here, right? So H is obviously going to be the last one, for sure, for sure. So let's just put that as 4, but it's still tied, right? Now, our next tiebreaker um, will be, let's do green. This one still has a carbon over here, right? But this one has the 3 hydrogens on it, right? So which one's more prioritized, this carbon or this hydrogen? Right, this carbon. So now this group is 3, or I mean 2, and now this group is 3, right? So now we connect 1, 2, 3, 4. So it looks like it's gonna, the priority is gonna be going where? To the right, right? So it's 1, 2, 2, 3. And we don't care about the 4 too much because the fourth is always going to be in the back. And that's going to be another thing I want to stress here is that the fourth is not always going to be hydrogen, right? Fourth priority is always in the back, right? So it's not always hydrogen. It's not always a methyl group. It can be anything. Again, just compare it atom by atom and you'll find it out. So fourth priority is always in the back, and that's because think of it as here's the three, and the fourth is in the back, right? So we can see the rotations over here. Well, this fourth one we don't care about, right? So this is what we care about. This is the three. This is the OH. This is the BR. This is the this is the ethyl, and this is the H, right? So we just care about the three in the front. And even more so, fourth priority is always in the back, but everything else can be wherever they want to be, right? The first priority can be to the on the plane, towards you, things like that. And another thing with this is if the fourth priority is not in the back, then you have to rotate it to make it in the back, to get it to the back, right? So always in the back. So manipulate it, rotate the structures, things like that. And that's where that gets tricky because a lot of students tend to they know that they need to rotate it, but they end up rotating it wrong. So everything is like all messed up, and that will give you your wrong answer, right? So that's what we're going to be going over mostly with our examples. So let's get to the examples. So let's do this. So we're still with stereogenic centers. Stereogenic centers. Hopefully, these titles make sense to most of you guys, um, because obviously there's like subcategories and all that, but hopefully these bigger, I I kind of put them all together so there's kind of like it's not just like 1 minute topics, you know what I mean? So kind of just like I guess put them all together that are semi-relevant or well these are relevant, but I feel like sometimes they're not. But hopefully it's okay. You can just skip it or scroll. Okay, so here we're gonna be let's see, we're gonna look for stereogenic centers on these. Um, so let's see, two over here. Okay, so we'll do stereogenic centers first, and basically we're looking for how many there are, right? So let me, oops, and then last one. So let's do this. Okay, NH2, H. Okay, so take a minute, label all the stereogenic centers you see. How many there are? Okay, so how many did I get? I got, for this first one, I got 2, I got 3, I got 2, and I got 0. So where's the 2 over here? The 2 over here are just, oh, actually, no, this is just 1. This is just 1, my bad. So this is just 1, right? 1, this one's 3, 1, 2, 3. And this one isn't 1 because this only has 3 groups, right? Because of that double bond. So you know that double bonds can never be a stereogenic center if because those double bonds obviously take up that one of the bonds. It's not gonna have 4 different groups automatically, right? And this one only has 3 groups as well because these two are identical, right? These two FO here groups as well. So they're not ones. So this one it has 2, one over here, 2, Same reason with this double bond, right? This double bond only has three groups. One, two, three. One, two, three over here. So, and this one has zero because over here. Now with the thing with cyclics is that you just cut them in half, and you see that these two are identical. So this one can't be one, and this and over here has only three groups as well, and two of them are the same H2, and same thing over here. Um, CO2H has a double bond to the CO, so no stereogenic there. So that's it with stereogenic centers. Easy peasy. Nothing too crazy. That, is that right? Okay. So let's do more over here. Genic centers. So now let's go with RNS configuration. So I want you guys to label R or S. Is that what I want you guys to do? Yeah. So let's see this. Oh, I choose. Okay. Okay. Oh, H over here, H3C over here, H over here. And these are all going to be the same, I think. CH. Oh, no, not the same configuration, the same molecule. So I think they're just all rotated differently. So oh no, they are different. Okay. H3CH2 C, and then over here, hopefully you guys really don't hear that molar in the background, because then I'm gonna have to view this video. So okay, obviously if you're hearing this, if this is what you guys are watching right now, I did not remake the video. Okay. Okay. So pause the video, take a couple minutes, and tell me if these are all R's, S, which ones are R, S. Okay? Okay. So I got um this one was an R, this one was an R, and this one was an S. So first, let's do each one of them, right? Let's do priority. So this is one, right? And then two over here, three over here, four over here. So it's going, it looks like it's going here, right? But it looks like it's going the S way, right? But what do we say about the fourth? It has to be in the back, right? And right now, this ethyl group is in the back. So we have to rotate it. And the way I rotate it, I'm going to do a different color so you guys can kind of see. I'll do blue. Is pretty much I draw the same things out, right? I draw the same thing out, but now I rotate it. So I want the one to stay, because I mean we're only rotating three things, right? So I want the one to stay because it's already in the right place, it's in the front. But now I just go like this. I just rotate it. Now this H is going to where this is. Now this CH, this ethyl is going to where this 3 is, and now this CH3 is going to where H is, right? So hopefully you guys followed that. So basically, H was over here. Now hydrogen's over here. Ethyl was over here. Now it's over here. CH2, CH3, and now CH3 is over here, right? So I just rotated them. I just, um, you know, one at a time. So now this is 1, 2, 3, and 4. Now the 4 is in the back because of the dashes, right? We know the dashes are gonna be in the back. So now that's an R, right? That's where I get our R from. So let's do the second one. So the second one, let's do this. Is the fourth priority in the back? Yes or no? No, right? So Again, these are pretty much the same priorities. We have one over here, two, three, four, but this four is not in the back, so we have to rotate it. So let's do purple this time. Let's draw the same thing again, right? So we'll have the same whatever. Um, and now we want to get this H to the back over here. So I keep the CL over here because that'll be the easiest. Rotate the H to where the CH3 is, CH3 to the ethyl group, and ethyl group to the where the 4 is, right? So now H is over here, CH3 is over here, CH2, CH3 is over here. So now we have 1, 2, 3, 4, and we still have an R, right? So things like that, rotating it, the best thing is, I think, is just, you keep one, you keep one state, and then you rotate the three, right? And it's super easy. Think of it. So I've never even used this analogy before because they never existed during um my semesters at ISI. Think of it as fidget spinners. Fidget spinners. They have three, right? And just add one. So those three can rotate. This is so fidget spinners. The three things it has, right? Those things can rotate, and you just the one we keep is it stays. So this is the CL, and this is the three. The three we're rotating, the fidget spinner that we're rotating. So wow. Okay, sorry about that, but it's I now that I'm thinking back to it. It just happened a second ago, but I regret mentioning it. But hopefully that helped. Hopefully that helped some of y'all. Okay, so this one, oh shoot, sorry about that. This one was supposed to be H, so hopefully you guys caught that. But let's do this anyways. So again, one, two, three, four, right? So now here's an interesting one. Instead of in the front, H is in the, I mean, instead of in the back, H, the fourth priority is in the front. So this one's super easy if we just 180 it, right? So let's do orange. Right now it's looking like an R, right? One, two, three. But since the fourth priority is in the front, we just flip it, so it looks like an R, but it's actually an S, right? So if if fourth is in front, 180 it. So S to R or R to S. So if it looks like this one, it looks like an R, but since it's in the front, we just 180 it, and it's an S, right? So that's the easiest way for that. You don't have to rotate it. You just label it as is, um, and then 180 it. So label as is, then flip, right? Label as is, then flip. When fourth is front. Okay. When fourth is front, label as is, then flip. That's kind of what I said here. I kind of just reset it. Okay. So it's very colorful. Hopefully all the colors are helping. Hopefully that fidget spinner analogy is helping. Um, but yeah, that's all with stereogenic centers with the RNS. You can do that for everything. And again, I can't stress enough, the fourth priority doesn't always have to be hydrogens, right? It can be a smaller molecule or a smaller functional group or whatever, right? So let's move on to um, what's the last one? Stereoisomers. So we talked about earlier isomers being divided into constitutional stereoisomers. Well, stereoisomers actually get divided into more parts. So it's going to have its own um, a little own little topic thing here. So it's divided into enantiomers, and diastereomers. And enantiomers are gonna be mirror images, mirror images, and diastereomers non-mirror images. And enantiomers also get more broken down into mesocompounds as well. Mesocompounds. Okay. Ooh, that's really ugly. So mesocompounds. So but that's all you need to know about enantiomers, diastereomers. Mesocompounds, I guess I need to explain that. Mesocompounds are going to be achiral, and it has within itself has two identical halves. Um, two identical halves. So it's not like a mirror image. Think of it as a mirror image within the molecule itself, and we'll see once we do a practice, it'll make more sense. So two identical halves within itself, right? And now just a little kind of a better way, or I guess a faster way, because sometimes you'll have a big molecule. So kind of like a fast way to do this is um, let me, with this with this little chart over here. So let's say R, R, S, 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 R. So, and they kind of go over here, right? Right. Oh, I should have used different colors. Okay, so going this way, if both completely switches, they're gonna be. Let me do different colors here because this is too much pink. So there's gonna be enantiomers, right? And everything else diastereomers. So that's easy, right? Diastereomers, and then this middle part is also diastereomers. So, and it makes sense because I mean, if it's completely flipped, it's going to be a mirror image, right? But if it's not going to be a mirror image. So that makes sense. And this bottom part over here actually is um, this one is enantiomers, but it's a meso compound. So, and that's where the two identical halves are, right? It's like a mirror image within itself. So that's why it's one. They kind of only one flip, you know. So not too crazy. And with the properties, since enantiomers are mirror images, they're gonna have the same physical and chemical properties compared to diastereomers, right? So not too crazy. And actually, let me write that down just to have it. Um, same physical, chemical properties, different and properties, right? Okay. So now let's do practice. And this one, yeah, this one's gonna be a good one. So let's do this one. Okay. So let's do these, and all these are, or no, one of them is, or most of them are going to be labeling disomers, stereoisomers, um, I mean enantiomers, things like that, or mesocompound, right? But mesocompound we'll do a little bit later. So stereoisomers, let's do this one. Um, kind of the same format we did with the constitutional and stereo, but let's do this. Arrange versus, and you do the same process pretty much. So don't get, don't get confused by it. I wonder. Hopefully you guys aren't really hearing that. That's a BR. BR. I apologize for the bad drawing. Um, but hopefully, just follow my voice. It'll guide you to what these are. Okay, last one. Let me see if I can squeeze it in here. Um, see. HCl. Out of all the days, this guy is mowing his lawn right now. You know what I mean? It's just one of those things like, okay, like, thanks, you know? Okay, almost done. Almost done. An HCl, H. Okay, so, okay, now label them. Take a minute, pause the video, um, get back to me. So, this is what I got. Let's do one we haven't done before. Okay, I got here, this one I got enantiomers. Two, I got diastereomers. Three, I got diastereomers. Four, I got, and this one was a tricky one because I didn't even tell you guys that there was gonna be one of these, but this one I got identical, right? So enantiomers, again, if we were looking at just the wedges and dashes, both of them switch, so that's like a mirror image. So both of these switch to thing, and we can even do the RNS thing, right? We can do here 1, 2, 3. This one is going R. This one's 1, 2, 3. This one's also going R. So now we can do on here, since we're not showing the fourth, which is the fourth priority in here is the hydrogen, obviously. So since this one's in the back, so we can assume that that one's in the front. So we just this one is obviously S because it's going to be the same priority as this, but just switch, and this one is also going to be S as well. So RR to SS enantiomers, right? And now this one, the stereomers, this one only one of them changed, right? So disclaimers, not both of them flip. Not they're not mirror images. This one is a good one because I picked this one because necessarily it's not necessarily well, I guess we can do this. This is trans and this is cis. Things like this, they're automatically diastereomers because we know we can't rotate around this double bond, right? So they must have had to break it. So if you broke it, that's a diastereomer because they're not mirror images anymore, right? So that's why, yeah, you don't need wedges or dashes, and there's no R and S, things like that. It just broke. And this one's identical. This one, let's see. This is the side that's different for it, right? Um, oof, what a mess. Okay, this H wasn't supposed to be here. Okay, so these, I'm gonna do a different color because there's too much salmon now. So this is what we're looking at over here. Um, right? And you kind of see that they kind of just switch spots. But if you think about it, fidget spinner, right? All those three just kind of rotated, right? So they're super identical because um, it's still they just rotated, and you can make they're not mirror images at all because they can be rotated, and yeah, so things like that. Um, Now let's do one with stereo meso compounds. So and this one will make much more sense. What do we really well? Which one is meso? So we'll have this is going to be two parts. So between these two, which one is it? Versus this one. Okay. And then between these two over here, so we're not comparing all four of them, we're comparing just two. So which one of this pair is meso, which one of these two is meso? So take a second, pause the video, get back to me. So I got this one and this one. Why? Because again, meso compounds are identical halves within itself, right? So if we cut this in half, these aren't mirror images, right? These aren't mirror images, but this one is, because this was wedged and now it's dashed, right? So if you fold that, those are mirror images, right? And this one, this doesn't even have any stereogenic centers. So this is not SC, not SC. So it's not even gonna be an enantiomer or diastereomer, right? So not S SC. And this one again is kind of the same as this one. This can be a meso compound because this can be wedged or dashed, this can be wedged or dashed, right? So easy as that. Meso compounds, again, it's just stressing this, it's with its own molecule. It's not compared to something else, unlike diastereomers and stereoisomers. So hopefully you guys, keep that in mind when you guys are looking for all these isomers, all these we learned, right? So with that being said, that's all I have for you guys. Again, these are the stuff we covered. You know, hopefully that helped. Hopefully that shed some light. Hopefully that was fun for you guys. So I'll see you guys next time, and thank you guys for joining me in this video. Bye.